Welcome, everybody. It's very exciting to be here and to welcoming you on this kind of, in Tacoma, fall, very much like a fall and breezy day. My name is Adela Ramos. I am Director of Communications and Partnerships at the Tacoma Tree Foundation. And before we begin our program, I just want to thank the Tacoma Create grant funding that makes this webinar and all of our educational programming possible. Thanks to this kind of funding, we are able to provide free programming, not only to Tacomans, but many of you are joining us from other parts of the country. So to people all over the country when we're able to do our programming online. So we're very grateful to Tacoma Create that this kind of grant allows us to fulfill our commitment to free trees and free education. So what we are going to go over in the next few minutes are the webinar logistics, the land acknowledgement, a very brief introduction to Dr. Brian Kane, who I'm very excited to introduce, and then Dr. Brian Kane will offer his presentation. We will have a period for questions and answers at the end. I'll go over that in a second, and then we'll just have some brief Tacoma Tree Foundation announcements as we conclude. So we want to begin with our land acknowledgement. It's very important here at the Tacoma Tree Foundation to acknowledge that we live, learn, and work on Puyallup tribal land. And one of the many reasons why we begin all of our programming with this acknowledgement is because we are invested in learning from our past, specifically from the cultural and environmental devastation of a colonial past, and making sure that through webinars like the one we are kind of fortunate enough to be able to attend today, we learn how to be better stewards of the land and keep in mind that we are on tribal land and that our kind of values and our commitment is to honoring this land. And so with that, we will segue into this webinar, Tree Failure, an Introduction to Arboreal Biomechanics. Dr. Brian Kane has very, very generously agreed to offer this webinar for us. Dr. Brian Kane is Massachusetts Arborist Association Professor of Arboriculture at UMass-Amherst. He has been dragging brush since 1989. He is an ISA Certified Arborist since 1997. And his work on tree risk assessment and tree worker safety, which are two of his main areas of expertise, has been published in numerous articles, and he frequently gives presentations such as the one he's giving for us today, not only in the US, but all over the world. And his scholarship has also been published all over the world. So we are really excited and fortunate to be able to learn from Dr. Kane today. Welcome. Thank you so much for being here.
Thank you very much, Adela. Appreciate it.
Absolutely. And I will now stop sharing and cede the floor to you.
Well, thank you all for being here. And again, thanks to Adela for inviting me to help have a conversation today about what we in the arboriculture community call tree biomechanics. Before I get started with the formal presentation, I just want to acknowledge some of the organizations that have been very supportive of our program at the University of Massachusetts and some of the work, research work that we've done that has made this presentation possible. So the Massachusetts Arborists Association gets top billing because they have paid half my salary at UMass. I wouldn't have a job if it weren't for them. And I've also been very fortunate to have received funding from the Tree Fund and the Florida chapter of the ISA. Those are two really important sources of funding for scholarship research projects that relate to trees growing in residential landscapes, which is not a common place to find funding. So we're really appreciative of the organizations that do support this kind of work. And I'll just pop this up for my contact information. And although I'm not in charge of our social media, it runs much better because of that. We have a social media presence that if you are on social media, you want to follow what's going along at UMass. We frequently post all sorts of interesting stuff that students are doing or research projects and career opportunities, those sorts of things. I'll also just point out that I'm happy to stay late today to answer questions. But if we don't have time to get to yours, or if you think of something in the future, please don't ever hesitate to reach out by email. I'm usually pretty good about responding within a day or so. So if you're not familiar with this term of biomechanics, sometimes people kind of combine tree with biomechanics reflexively, but that's not really the case. Biomechanics is a discipline that is the kind of putting together of biology and Newtonian mechanics. And so this is essentially the study of the physical or mechanical aspects of biological organisms. So whereas engineers, build structures or design structures or machines or components of machines or tools, there are laws of physics that any organism has to abide by, just as a built structure or a tool does. So when we think about trees, we are looking at them not only as a biological organism, but also as a physical structure, one that has to abide by the laws of physics, just like, a bridge or a building does. Most of the time that arborists look at or are thinking about tree biomechanics, they're specifically thinking about it in the context of tree failure. And so that's part of why the title is for this presentation, Thinking About Tree Failure, because that's how arborists are typically using the kind of thoughts that go into biomechanics. So this obviously is a tree that has failed already. And this is something that hopefully hasn't happened to you, but it is definitely something that arborists deal with on a regular basis. For a long time, we were mostly thinking about this sort of failure as a function of defects. And so the defect that's most obvious in the screen here right now is this, a lot of decay in this tree trunk. But that's really only one small part of understanding this concept of failure and why trees fail, or why certain trees have a greater or lesser likelihood of failure. So this concept of failure applies to any structure. It's not just trees. And you can basically think of it as the loads that a tree or any structure experiences. When they exceed the load-bearing capacity of that structure, that's when failure occurs. So if you were to, you're sitting at home or in your car and you have a pen, if you attempted to bend the pen or pencil, it offers a certain amount of load-bearing resistance. And when you get to a point that you have exceeded it, then you're going to snap the pen in half. Now, this is a really nice pen, so I'm not going to do that. But this concept of failure applies to anything. Loads and load-bearing capacity are what you need to understand. There's another pair of words that I'm going to get to in a few slides, which is a sort of a repeat of this, which is failure occurs when the stress a structure experiences exceeds the strength of the material that the structure is made of. But we'll get to that in a second. So I basically want to take the time today to review the mechanical concepts in a very, very kind of brief way that you see listed on the screen here. So if you have a degree in civil engineering or mechanical engineering, then you might appreciate the tree stuff, but all of the mechanical concepts here are going to be pretty rudimentary. So normally, if you were an engineering student in college, you would have, 3 or 4 classes that would cover these topics. So we have 45 minutes. So we're going to necessarily have to give a very, very brief instruction on each one of these. So the term load is kind of a catch-all term. It's a generic term that, for our purposes, when we're thinking of tree failure, we basically think of loads as either forces or what are known as bending moments. So a force is pretty straightforward. It's just a push or a pull. And you can think of it as being applied to the outside of a structure. So again, we're going to think of trees today. So pushing or pulling on a tree, not from inside, but that occurs outside of that tree. So just as an example here, this silver maple in the screen, gravity is pulling down on it, just like gravity is pulling down on all of us. But the tree doesn't sink into the ground because there is an opposing force that is in the opposite direction of gravity, and that's offered by the ground, which pushes back up on the tree with an equal amount of force. So you probably have heard the phrase equal and opposite forces. Maybe you've heard of force couples. These 2 arrows that are shown in yellow are just indications of the forces that the tree is experiencing right now. Again, gravity is pulling down and the ground is pushing back up. So you know that the forces are equal and opposite because the tree isn't moving. It's not sinking into the ground and it's not kind of floating off into space. When these 2 arrows are lined up like this, they basically don't cause any bending. So you can imagine these 2 arrows are pushing against one another, and that's just trying to compress the tree. If the 2 arrows were pulling away from each other, then that would be pulling apart, trying to stretch the tree. So if you were to tie a rope, let's say, to the tree and try to pull it out of the ground with a crane, then there's going to be an arrow of gravity pulling down, and the ground is also going to resist that. So there would be an arrow from the ground in the opposite direction that's shown on the screen. And then there would be a force going, an arrow going up. That is the force that the crane is applying to the top of the tree. So in all of those cases, the forces are lined up with one another. So there's no bending involved. It's just either tension if the forces are pulling apart, or compression if the forces are pushing together. But for many applied forces, for many of these pushes or pulls, there will be a distance between them. And I'll show an example of that in the next slide. And that distance is what we refer to as a lever. And when a lever is present, then the force gets converted into what's called a bending moment. And that amount of bending, that the magnitude of the bending, is the amount of the force times the amount or the distance of the lever. So with trees, it's quite often that bending moments are responsible or largely responsible for failure. And so there's a lot of little arrows on this diagram in this picture, but this is the same tree we just looked at, except now I haven't put the arrows showing gravity, although gravity is still acting on this tree, but I've just left those arrows off for right now. Instead, I've drawn a whole bunch of arrows acting on the little leaves and the twigs and the branches as the wind pushes on the crown of this tree. So the force of the wind is called drag, and we'll get to that in a couple of slides. But you can imagine, as the wind is blowing on this tree, the tree is getting pushed or bent. It's not sliding through the ground, but the branches are bending away from the wind. So again, I'm using this word bending now and not pointing out, sorry, I'm using the word bending because there's now a bending moment, because the wind, the force, the drag is acting on a lever over a distance. The reason the tree is not getting pushed sideways through the ground is because the ground now is pushing back in the opposite direction. So the ground is offering this equal and opposite reaction, pushing against the direction of the wind. Remember, gravity is still going on, and the ground is also still pushing up on the tree against gravity, but I just haven't put those arrows on this slide. To make this a little bit simpler, we are not going to try to calculate the drag and the bending moment based on every single one of these little arrows. We're going to simplify it and just say, okay, we're going to add up all those little tiny arrows that indicate the drag and all of those little tiny arrows that indicate the force that the ground is exerting on the roots. And we'll just keep it simple and make 2 arrows. So that's those 2 horizontal arrows you see. They are in the opposite direction. So one points to the left, the other points to the right, but they are no longer lined up with one another. There is a distance, or this lever, that exists between them. And that's where you have, this is where you get bending moments, when the forces don't line up with one another. They're still equal in magnitude and they're still opposite in direction, but now they are not lined up. And as a result, the lever causes there to be this sort of rotation. That's what the bending moment wants to do. It wants to rotate the tree around the point in the ground where the roots are. Now, again, it's obviously not rotating fully, but it still is going to bend. And you can see that obviously on a windy day. Just to put some numbers, these are effectively made up numbers, but it's not totally unrealistic that you could have a lever 50 feet long, depending on how tall the tree is. And depending on what the wind speed is and the area of the crown of the tree, the drag could easily be 1,000 pounds. So you then have a bending moment of 50,000 foot-pounds. Force times distance, force times lever. You can also have bending moments that occur because of gravity. So remember, we showed on the previous slide, switch this to a pen. Remember, we showed this on a previous slide that the total weight of the tree is being opposed by the ground. And so these arrows that I'm drawing, they're lined up with one another. They're equal and opposite, but they're basically lined up. If we just wanted to instead imagine the weight of this big, huge branch here that goes out around the rest of the screen. So just this part on the side over here, you know, its weight, you can think of it as acting somewhere out about the midpoint of its length. And that's not going to be perfectly accurate. But if you imagine that, it's being held way back in here where the branch attaches to the trunk. And so there is a short little lever here. It's not long, but there is still a short little lever here that again causes a bending moment that tries to bend or rotate this whole branch around the branch attachment, as if it were going to split open that branch attachment. You may have seen this. If you're an arborist, you've definitely seen it, but you may have seen this just, you know, on trees after a storm where there are branch attachments that have separated, failed, and the branch is laying on the ground, but the tree is still standing. It's just lost a branch or maybe 2. So there can be bending moments that result from wind, but there can also be bending moments that result from just the force of gravity. So I mentioned earlier that failure occurs when the load exceeds the load-bearing capacity. And then I said that there's another pair of words, which is this: failure occurs when the stress exceeds the strength. So I want to just give a quick overview of what this concept of stress is. And the reason stress is important is because it basically takes the forces, the loads that are acting on the outside of the tree, so wind pushing on the tree or gravity pulling down on the tree from the outside, the amount of those forces, the magnitude of either the force or the bending moment, gets distributed across the entire cross-sectional area of the trunk or a branch or whatever part of the tree you're interested in looking at. Even like, the stem or the petiole of a leaf. If you were interested in trying to calculate the stress that that petiole experiences, you would want to know the drag that's on the leaf itself, and then how much cross-sectional area there is in that petiole. And then you can calculate the stress basically just as diagrammed on this picture here. So the stress is a way of normalizing a load over a certain area. So when we think of stress, the easiest way to remember it is stress is always going to be in units of pounds per square inch. Or if you're using metric system, then it's going to be newtons per meter or newtons per millimeter, square meter. So this pounds per square inch is just the force. And let's look at these two cylinders we have here. One of them is the weight of that entire tree that we just looked at. And one of them, let's just pretend, is a small branch on that tree. So the weight of the tree, again, this is a made up number. Let's just say it's 10,000 pounds. And if we looked at the trunk and just imagined it was a circle, it's not a perfect circle, but we'll keep this simple for right now. Let's just say that area of the trunk is 100 square inches, which means the stress that the trunk experiences is 10,000 pounds divided by 100 square inches. And that gives you 100 pounds per square inch. So these large arrows up at the top and the bottom of each of the cylinders, we can think of those as the external forces. So gravity pulling down on the tree, and then this down here is the ground pushing back up on the tree. The little arrows inside that cylinder are just indicating that those bigger arrows get divided up among the entire cross section. So this is thinking about this in terms of square inches. There is 10,000 total pounds of force or weight, but that 10,000 pounds gets divided up by the 100 square inches. And that's where you get, again, 100 pounds per square inch. So you would rightly think of this 10,000 pounds is a lot of weight. That is a big number. 100 square inches is also a pretty big number. If we look at the branch from that same tree, this is a much smaller branch now. So it's only 100 pounds of weight, but the branch has a smaller cross section. So as a result, that 100 pounds only gets divided among 1 square inch as opposed to 100 square inches. So the stress in both of these cross sections, in both of these cylinders, is exactly the same. One has a lot more weight, but a lot bigger cross section. The other one has much less weight, but a much smaller cross section. And so the stress is in fact exactly the same. Taking this one step further and thinking back to failure, this definition, failure occurs when the stress exceeds the strength. If the wood in these two cylinders here, one representing the trunk of the tree, one representing a branch in the tree, if the wood were exactly the same strength, because these cylinders have the same stress, they would have the same likelihood of failure. And I don't want to go too far off topic, but especially for arborists who do tree risk assessments, they know that it's really important to assess the likelihood of failure potentially of many different parts of a tree. So it's rare in a tree that you would assess likelihood of failure only at one particular location, because there could be many parts of a tree that might have some likelihood of failure. And your responsibility as the arborist is to make sure that you are looking at each of those parts and trying to decide which one has the highest likelihood of failure. And then the process of risk assessment goes into a lot more detail. But this is why this is relevant here when we think in terms of stress, because we want to look at not just one spot on the tree. we usually have to look at multiple places to assess the likelihood of failure. So that's looking at a very quick introduction to the loads that a tree experiences. We're going to come back to loads towards the end of the presentation. But now I want to just switch gears and look at load-bearing capacity. So again, failure occurs when the loads exceed the load-bearing capacity. And we want to know what goes into that load-bearing capacity. What makes something a higher load-bearing capacity and something else a lower load-bearing capacity. So that the two main factors are the shape and size of the cross-section and the material strength. So whatever that cross-section is made of. For our purposes, we're thinking about trees. It's not perfect circles all the time, and many cross-sections can be elliptical in cross-sectional shape, and many times it's not even close to a regular cross-section, that the shape could be kind of odd. So for the sake of making this relatively straightforward, we're going to just assume everything is circular in cross-section, and because of that, the size factor that we're interested in is just the diameter of the cross-section. So if the diameter increases, the load-bearing capacity increases. And in fact, it increases as a cubic function, which means if you were to double the diameter, so let's say you had a 10-inch diameter cross-section and you went up to a 20-inch diameter cross-section, doubling the diameter, when you think about that effect on load-bearing capacity, you have to cube it, which means you're multiplying doubling 2 times 2 times 2. 2 cubed is 8. So doubling diameter increases load-bearing capacity by a factor of 8, which is a really big increase. If you imagine finding a branch or a small twig laying in your yard, and if you know anything about different species and the wood that those species formed, you know that material strength, the wood of some species, is stronger than the wood of other species. So especially if you have experience with this, just imagine finding a branch that is made of the weakest wood you could possibly imagine. So in most cases, it would be something like a willow or a poplar or an aspen or something like that. But imagine that it's 2 inches in diameter, and then try to imagine bending or breaking that branch. Now you can probably bend it, but a 2-inch diameter branch is going to have a pretty large load-bearing capacity. Now, alternatively, imagine a branch of the strongest wood that you could possibly imagine. So some kind of oak or a hickory, and make it a really small cross-section. So make it just a 1/2 inch diameter. You can bend that pretty easily, even though the wood itself is really, really strong, but it's such a small diameter cross-section. It's only 1/4 as large as a 2-inch diameter cross-section. So that means the 2-inch diameter cross-section, remember, it's whatever magnification you make is going to be cubed. So it's 4 times 4 times 4. 4 cubed is 64. It's 64 times the load-bearing capacity, which is why it's much harder to bend a 2-inch diameter branch than a 1/2 inch diameter branch, even if the wood strength itself is much greater in the smaller diameter branch. When we think about this likelihood of failure, then, we are matching up the stress that a component or part of the system experiences, and each of those components, what their material strength is. So, for example, this is a research project that we had at one point where we were measuring tension in the rope here and seeing how it bent the branch up and down a little bit. And if we were interested instead of pulling on this rope as hard as we possibly could with a winch or something and seeing what was going to break first, we would need to compute the stress in the rope and compare it to the strength of the rope, and then the stress that's in this shackle here and the strength of the material, which is made out of steel, and then the stress in this sling, this is made out of polyester. So what's the strength of polyester? And lastly, the stress in the wood, and what is the strength of the wood? So when you were thinking about likelihood of failure, even in a tree, and we're going to get to this in a second, because wood has different strength properties depending on what type of stress occurs in it, you need to match up stress and strength. And that's just a more nuanced way of saying we're matching up the loads and the load-bearing capacity, because the load-bearing capacity depends on size, shape, and material properties. So let's think specifically about wood here. As I already mentioned, the strength of wood can vary by the species, but even within a species, the strength of wood can vary by the growing conditions. So a red maple, for example, I know that they're not as common out in the West Coast, but red maple is common in, from all the way up in northern Maine on the East Coast, all the way down to central Florida on the East Coast. So it has a huge range, and not just on the coast, but it also is farther inland, so west of just the coast. Red maple is a very, very common species, and depending on where it's growing, so depending on the length of the growing season, depending on the soil texture, depending on the amount of precipitation, depending on all of those different factors that affect how it grows, the wood strength can be very, very different in two different red maples growing in two different places. And in fact, the wood strength can be different even in the same exact red maple, depending on whether the wood is newly formed wood or older wood or juvenile wood or mature wood, or wood that's formed in branches, or wood that's formed in roots, or wood that's formed in the trunk. So the amount of variability that is present when we think of wood strength values is quite high. Even in the exact same tree, in the exact same growing condition, the location in that tree can cause wood to be much different, stronger or weaker wood. So it's quite variable. Now, this last factor down here is the type of stress, which I just mentioned earlier. And then we have to go through a little bit more to understand this. There are different types of stress when a tree is being loaded. So we mentioned before the difference between tension, a tree that's trying to be pulled apart, versus compression, when a tree is being subjected to the pull of gravity and the reaction force of the ground. So wood is actually quite a bit stronger when it is being pulled apart than when it is being compressed or pushed together. And if you were to try to bend wood like this, rather than try to like what's called shearing the wood, sliding the wood, the fibers next to one another, wood is much stronger when it's being bent than if it were being sheared. And so you can oftentimes see the different types of failure manifesting depending on what stress exceeded what wood strength. So for example, if we look at these two images here, you may have seen this failure in the left-hand image, which is like a split that kind of goes right through the center of the trunk or the branch. This is a shear failure. This is when the wood is trying to slide, fibers are trying to slide next to one another. The greatest amount of that stress is right in the middle of the cross section. It's called the neutral plane of the cross section. And this branch on the left technically has failed, even though it's not hanging, it's not falling on the ground. It has failed because it's failed in shear, but it hasn't failed completely in bending. In contrast, the right-hand side image, that branch is no longer there. So you can see the fracture here. The branch is laying on the ground. This is bending failure. So in that case, the bending stress that was applied was greater than the bending strength of the wood. In the left-hand image, the bending stress was not greater than the bending strength of the wood, but the shear stress was greater than the shear strength in the wood. So again, it's a kind of a long-winded way of saying wood properties in trees are highly variable. And as importantly, there's many different types of stress that may cause a tree to fail. So it's important to know when you are doing risk assessments, thinking about all of these different possibilities. So it's a much more systematic process than simply, looking at a tree and giving a gut reaction to something. So returning to the concept of loading, there's lots of different ways to characterize loads. So you can think of, I've already used this term, magnitude. So that's the amount of a load. But there are other ways to think about loads, like how frequently a load is applied. So for example, if it's gravity just pulling down on the weight of the tree, that's effectively what we would think of as a static load. It doesn't really change. But on the other hand, on a windy day, the wind is kind of pulsing or gusting. It's not really a static or unchanging load. It changes quite a bit. And those are dynamic loads. And this is important because unlike most engineered structures or components of tools or structures, trees respond quite differently to loads in general. So they usually they deflect or they move a lot more than an engineered structure. But in particular with dynamic or static loading, the tree is going to respond differently, and it's very obvious, much more so than in an engineered structure, because they tend not to move as much. So I said this on the previous slide, but it's worth kind of just stating it again for clarity. The types of loads are generally static or dynamic. And static just means that they don't change very much over a short period of time. So for example, the weight of the tree will change as the moisture content in the wood changes, as leaves or needles are dropped or regrow, as branches break off. Those are all factors that could cause the weight of the tree to change, but those tend not to happen in very short periods of time. Even in the example of precipitation accumulating, whether it's liquid precipitation or frozen precipitation accumulating on a tree, that tends to occur over a period of hours rather than a period of seconds or minutes. So we think of those again as static loads, not changing very much in short periods of time. In contrast to that is, again, this dynamic load where the magnitude, the amount of the load, can change pretty dramatically in very short periods of time. So the easiest one to visualize is just imagine a tree on a windy day. You can see it moving back and forth quite a bit as the wind speeds up, slows down, maybe changes direction a little bit. So that is the classic example of a dynamic load. For arborists who are working in trees, another good example of a dynamic load is when you are rigging a tree. So you're pruning branches or maybe removing the entire tree, but you can't simply cut and drop the branches down because there's a target beneath you. Then you would use ropes and blocks and pulleys to lower the branches that you're pruning, lower them under control. And sometimes when you do that, there's accelerations involved that as the rope tries to stop or arrest the fall of the piece of wood you just cut, there can be this kind of shock load that also is a dynamic load. Its magnitude changes very quickly in a very short period of time. When we're thinking about dynamic loads, wind again is probably the best example. So we're gonna use that to kind of illustrate a couple other key concepts. And when we are imagining the force of the wind, that's, remember this term we used before called drag, we need to understand how much drag is present. So that's going to be largely determined by the velocity of the wind, the speed of the wind. It also depends on these other factors in the equation down here, and I'm not going to go through these in great detail, but A just stands for area, and that's the frontal area that the crown projects. Like if you could take a picture of it and count the pixels that had leaves or twigs or branches. And CD just is a shorthand for what's called the drag coefficient. And the drag coefficient basically is a measurement of how easily a fluid can move either through a structure or around a structure. So you can think of it as kind of measuring the tree's aerodynamics, how easy the fluid or the air can move around a tree. And again, this last one is V stands for velocity. So velocity is the main factor that influences drag in trees. And that will tell you how much drag, how much force the tree is going to experience. But because the wind is a dynamic load, we also need to understand this thing called gust frequency. And that gust frequency is basically how many pulses of wind interact with a tree during a certain period of time. So again, on a windy day, the wind speed may start out at 20 miles an hour, but then there's a pause and it might go back down to 5 miles an hour. But then a few seconds later, it might go back up to 25 or so miles an hour. So let's look at this in terms of a graph, which is going to come up on the next slide. We're going to just demonstrate how those pulses of air are moving with respect to a certain amount of time. The frequency of the wind, this gust frequency, is just how many pulses of wind there are in a certain period of time. And usually think about it in terms of minutes or in terms of, probably not seconds, but if we think about it in terms of minutes, it's a little bit easier to visualize on this graph. So here's 2 minutes, elapsed time, 20, 40, 60, 80, 100, 120 seconds. And here's the wind speed. This is measurements from a research project we were working on several years ago. So here's the wind speed, miles per hour. We don't quite get up to 14 miles per hour, but you can see the wind starts out somewhere below 4 miles per hour, and then it accelerates and gets up to almost 12 miles per hour at about 10 seconds in. Then it slows down, and then at about 25 or so seconds, it speeds back up, and it's over 12 miles per hour. Then it goes back down, then it comes up a little bit. So you can count these gusts, these periods of pulses of wind that would be pushing on a tree. So there's 1, 2, 3, 4, 5, 6. And if we count this little one, then we've got 7 gusts of wind in a 2-minute period. And so the frequency is just 7 gusts divided by 120 seconds or divided by 2 minutes, however you want to think of that. The tree responds, and again, if you've ever been outside a windy day, which presumably you have, you watch trees or at least tree branches swaying around, and that is what we call the sway frequency. So how much the tree moves and how quickly it moves, the number of times it's going to sway after a force like drag acts on it. The other thing we need to know is once that force stops acting on it, how quickly does the tree stop swaying? And this is something called the damping ratio. And we'll illustrate both of these things with some videos and some graphs. So here's the tree. This tree obviously has no branches on it. It was part of a research project, but it's just to illustrate that, we pulled on this tree with a rope and then we watched it sway back and forth. And we're measuring how many times it sways in a certain period of time. So if we look at this in terms of a graph, then again, here's the elapsed time, starting at time equals 5 seconds and going up to 23 seconds. So it's 18 elapsed seconds. And how many times does the tree sway? So this sway motion, this is just a back and forth motion as the tree is coming through center, going backwards, coming back through center, and then going forward. So there are 1, 2, 3, 4 sways, either on the positive or the negative side of that equilibrium point, the resting position. So the sway frequency is just the number of sways divided by the number of elapsed seconds. This graph is putting together both of those both of those frequencies, the gust frequency and the sway frequency. The sway frequency is this solid line here, and it's our 4 sways in that 18-second period. You can see from the wind frequency, though, we basically only have this one gust of wind that goes up and then comes back down and then maybe starts to go back up. But because the gust frequency was so much slower, it's not going to continually push on the swaying tree. They're out of sync, if you want to think of it that way. And this is important because a dynamic load, one that acts at a frequency, has the possibility of moving the tree a lot more than a simple static load. If the wind frequency, the gust frequency, and the sway frequency were similar, then it would be kind of like pushing somebody in a swing, where you would push them as they reach their maximum backwards motion. You can give them a push and then they swing forward. Then you wait until they come back and then you push them again. And by doing that, even if you're not pushing them really, really hard, you can still get them to start swinging quite a bit because you are pushing them at the same frequency that they want to swing back and forth. So this is when engineers design structures, they're very aware of this sway frequency because they want to make sure that they don't build a structure that has the same sway frequency as the wind frequency, the gust frequency, or the frequency that an earthquake might shake the earth at. The damping ratio is for a structure like a tree that is swaying back and forth, that's moving. The damping ratio is basically a measurement of how quickly the tree stops moving. So how well it can dissipate the energy that the moving wind kind of imparts to the tree. So if you watch a tree again on a windy day, it will sway back and forth, but then it will eventually slow down and stop. And that is this process of damping. And so how quickly that occurs, how many sways does the tree do before it stops, that also influences likelihood of failure. So a tree that continues to sway means that there's a good chance the next gust of wind is going to push it as it's swaying, which means it might have a greater likelihood of failure. But if a tree stops quickly, then the next gust of wind has to kind of start the tree moving all over again. So it's less likely to cause the tree to fail. And this video is going to show the same thing. This is from a series of tests we did a while ago where we were pulling trees with a winch and then releasing them. And so you can watch the trunk stops swaying pretty quickly. The branches continue to sway, and that's because the branches are smaller in diameter, and so they're more flexible, which means they're going to keep moving, which is a good thing because that means the trunk itself has a lower likelihood of failure. It stops swaying. So the next gust of wind would have to start it moving all over again. and this is just, again, an illustration of the damping ratio. When something stops moving more quickly, it has a lower likelihood of failure in general. So this is a graph just showing the effect of that damping ratio. Here's the tree being pulled initially and then released, and it kind of sways back and forth a couple of times. And then it kind of settles into this back and forth motion where eventually, after it looks like 13 seconds or so, the tree has basically stopped moving. And that's, again, a relatively small number. We would say this tree is heavily damped. It has a high damping ratio. So I want to make sure I left enough time for questions. And that is a very, very, very quick overview of, like I said, several college level engineering courses that I am not qualified to teach, but I'm fortunate that I have some friendly colleagues in the engineering college who are always happy to help out. And I'm happy to take questions on any of that stuff.
Thank you so much, Brian. I was actually, the view I have is of a cedar, a fir, a birch, and a chestnut, and the wind has been gusting the whole time that you've been speaking. So I was able to apply from my very limited knowledge some of what you were saying. So thank you so much. That's already, even the idea of wind as a load-bearing element has changed my sense of what I need to think about when I'm looking at a tree in the wind. So thanks so much. Everyone, as a reminder, please use the Q&A box if you have any questions for Dr. Kane. Okay, we have one coming in. First of all, great presentation. Can you recommend additional training resources on this topic on how to apply it in practice?
Yeah, that's so good question. Thank you too. So the short answer is that there are resources that arborists use primarily when it comes to like tree risk assessment. The one that immediately comes to mind is one that I'm actually helping out with, which is the Best Management Practices Guide for Tree Risk Assessment. And so this is available on the ISA's website, which is isa-arbor.com. And the Best Management Practices Guide goes through in a little more detail than we have, in the hour, many of the concepts that we've discussed today. It's a little bit in the future. I'm working on a little book to kind of go into some of this in more detail, but that probably won't be out for a couple of years. So I would say the BMP is probably the best starting point.
Great, thanks. And I did type it in the chat, not the URL, but I'd be happy to send that out to participants after. And any other resources that you'd like to share with them, I'm happy to email everybody afterwards. We have another question. What are some of the factors that affect damping? Oh, yeah, another really good question. So the main factor for deciduous trees is the presence or absence of leaves. There's been a bunch of studies that we've done and others have done that have illustrated really, really well how much less damping there is when a deciduous tree doesn't have its leaves. And in fact, it's so much so that it's way more different than you could do by pruning, for example. So a lot of people, and it's not necessarily wrong to prune a tree to try to reduce likelihood of failure, but the presence or absence of leaves on a deciduous tree kind of completely obliterates any effect of pruning that you could have by removing branches and that sort of thing. So the leaves is the most important thing on a coniferous tree, or a tree that doesn't drop its leaves, an evergreen tree. It's usually the number of branches and the distribution of those branches. So the
if you have fewer branches, for example, and they're located mostly up at the top of the tree, then the damping ratio is generally going to be less than if you have a lot of branches that are kind of distributed all along the length of the trunk. So if you've ever rigged a tree for removal, for example, you know that removing all those branches is usually the easiest thing to do, because then you can cut the top out and drop it without having to get hung up in the branches below you. But if you don't rig it properly and you get one of those shock loads, and you can look at videos of this on YouTube all day long, the tree will start swaying really, really violently. And that's because there's pretty much no more branches to help dissipate that energy that you're creating by dropping the top on on a rigging system. So leaves and the number and distribution of branches, you basically don't want a single like cantilevered beam. The more you can divide that tree up into other parts, smaller parts, the damping ratio is generally going to be higher.
Thank you, Brian. We have two more questions. Hi, Brian. I often hear community members express concern about the twisting motion of large trees, often Douglas firs. Can you speak to that from a failure perspective?
So yes, I think I can, Sarah. That's another good question. So there's another type of stress that I didn't describe, which is called torsional stress. And torsional stress occurs when there is something called a twisting moment. So instead of a bending moment like this, a twisting moment is one where you're literally trying to twist the trunk. And torsional stress occurs when that happens, and wood tends to be a lot weaker in torsion than it is in bending. The thing that's the reason you don't see too many trees failing in torsion is because it requires that twisting moment requires some kind of asymmetry in the crown that would cause there to be loading on one side of the crown but not loading on the other, which would cause the crown to try to twist. So the times I could imagine that happening, like if you imagine a Doug fir, for example, or any X-current tree, Doug fir, Sitka spruce, those sorts of things, where you remove branches only on one side of the crown. And doing that means one side of the crown is not going to get loaded at all by the wind, but the other side of the crown is going to get loaded quite a bit. And as a result, you will get this kind of twisting. So it's rotation this way as opposed to bending that way. And the situation when torsional failure, I think, is more likely is when you have some kind of asymmetry in the crown that would cause that twisting moment to be more problematic.
Thank you, Brian. And then one more question. How often should trees be pruned?
So that is a loaded question. And it would require a long answer. The short answer is trees should be pruned as often as is needed. And what goes into that is factors like, what are your pruning objectives? What is the species of tree? What is the health of the tree? How old is the tree? What are the growing conditions that the tree is experiencing? There's a lot of different factors you have to assess to know when is the appropriate time frame. Because it can vary dramatically depending on all of those factors, and there isn't a nice kind of straightforward answer, unfortunately.
Thank you. And Sarah saying thank you for the answer as well. And as a matter of conclusion, we always just like to remind attendees about our upcoming programming, as well as the fact that this presentation has been recorded and will be uploaded to our YouTube channel. So if you haven't already visited our channel, you'll be able to have access to this webinar again, and of all the other webinars we offer. We just had one with the Last 6,000, an advocacy group in Seattle that is protecting majestic heritage trees in Seattle, and we'll be uploading that very soon. So thank you everyone very much. Thank you again so much, Dr. Brian Kane. It's been a real pleasure. And yeah, we'll be in touch with any resources that Dr. Kane wants to share with everyone. And if you have any questions at all, you know where to find me. Thanks, everyone.